Okay, so if I manage to move this, okay, perfect. So the first thing I want to start looking at in this ANOVA chapter is the difference between the variance and the variability. So by Google's definition, variability means the lack of consistency, while variance is the average square deviation from a random variable mean. So what this essentially is telling you, and checking out another one, the variance is the expectation of a random variable, while the variability is the extent of how much a distribution may vary from its average. So that being said, we can first off delete my annotations and move into our ANOVA. So, and I'm sorry, I'm starting with theory. I think it's important for you guys to understand what ANOVA exactly measures. And first off, you have to remember that ANOVA is when you have two or more means that you're trying to compare. So in this case, it could be usually it can be like mean low, mean medium, and mean high. So say for example, you give out a survey and you ask people how happy are you? So you give them like um, five different options. And then you give them a bunch of other tests within that same survey. And then you say, the people who, what is the difference in the mean of how much chocolate they consume in a week of people that rated the mean of one. So let's do mu one equal versus let's actually type this out. So do mu of one versus the mu of people who scored two or gave themselves a two versus mu three versus mu four versus mu five. And then you'd like rate them and how much chocolate they consume per week. And you could see if there is any sort of difference in happiness of those who rated themselves happier and those who did not rate themselves happier and how much chocolate they consume. That is a very stupid example, but that's what the ANOVA test essentially it's trying to do from my understanding. You're trying to see if there is any variability between groups. So so ANOVA bases itself on the F ratio, which we will see the formula a little down the road. And the thing you need to know is that the F is large enough, you reject the null hypothesis, but these tests usually already give you a p-value, so you don't have to really be thinking much about the F statistic. Uh, so this is the F statistic formula. And these formulas I really didn't understand that much in depth, but I know for a fact this SST formula, and you can actually go talk to the teacher about this because I think I am not apt to explain it, but you can see it here in action. Uh, because what it's telling you, it was summa of your x bar or your y in that case minus your minus your population mean, I'm guessing. But again, don't take my word for it, but just know that if you ask the teacher this SST, you're seeing it here, and that this NJ is this, and then your XJ is this, your YJ, and you square it here. But I don't know exactly where that 22.3 comes from. So again, don't take my word for it. If you want to understand it, go ask the teacher. But just know that if you want to try to make some sense out of it, these formulas are like what is happening here in these ones, in these three, can be explained using these formulas. But again, it's better if you ask the teacher. I don't feel qualified to explain what is exactly going on here. So next up, you have your conditions. These are super simple. Uh, so the first one is that all groups should have an approximate normality. You do this usually by testing if their histogram looks like a bell curve. If it does, you're good. Then equal variance. So the best way to do this is you plot a bunch of box plots and say I'm gonna pause this. Give me 1 second. So anyways, that was that was hard using just my touchpad, but um this word essentially means that, as you can see here, all of these are pretty similarly shaped, and the medians are roughly at the same height. This one's a little lower, but it doesn't matter. While this one here, they're all over the place, and this would not comply with condition number 2. And then condition number 3 is that they are independent. If it tells you they're independent, that's great. And you can also use these two, but in any case, these are the conditions you need to perform an ANOVA test. So again, here the teacher gives us a couple examples. So this is a bell curve. Ignore that little thing I did. There's a bell curve, and down here you can see the box plots. They're pretty similar. So you should be good to do an ANOVA test if this looks okay. So going back to our actual examples, we're going to be looking at the truancy dataset. We've worked this, I think, like for 3 of our blocks, so you should be already pretty familiar uh, with what it tells you. It is a program that you gave. I'm pretty sure like high school students, and then you wanted to see whether it affected them. What happened here? Give me 1 second. I probably didn't open this correctly. Okay, I got it up and running. It was just that I have it loaded as truancy 1, and it is true. And this code I copied was truancy normal, or like truancy not 1. So next up, again, we've seen this before, although I don't understand necessarily why I think this might be wrong, because usually for the truancy one, we used to do post percentage minus pre percentage. Um, so I'm gonna go ahead and let's uh all of my code is based off the teacher, but we're gonna change this tiny little detail because we usually have done the difference post minus pre, and it makes complete sense because we're trying to see if something happened to the applied program. So we're gonna just change that around. So we copied this over, and we also copied this code over. So essentially, this is just a df.boxplot. We saw that in block 1 with the teacher. You didn't see it in my reviews, but it is super simple to do. In any case, it's here. So you essentially tell it, looking at the column diff separated by grade. So you're going to see that you have up here like K3, 6. So you can see that exemplified here. And next up, we're going to directly copy a code from the teacher within the recording because honestly, it's nothing too complex. It's just a code. Because if you see here, number 9, it's just like randomly squished there. It means that there are probably no values. So the teacher does something here. We can go ahead and just delete this. We could have also done drop NA. I'm pretty sure that would have worked. But for all intents and purposes, let's keep it simple. Let's not deviate too much from what the teacher did. We are already deviating quite a bit using a different df_diff. So let's keep going and just know that we dropped column number 9 because there was nothing there. So next, again, these are codes you should just like copy paste. They're here. I'm pretty sure I'm gonna give access to this document later. This is using the df.groupby function. In order to using this, you can input the NP mean, NP standard deviation, and len. So you can see it here this is gonna, so you see here your standard deviation, the length of each value, and length of 9 would have probably given us 0. There was nothing there. And they give us the mean. There are a lot of native means, which is strange. It probably was that I think there might be a issue with the data, but honestly, if you follow the code I'm giving you guys, you should be good. But just take everything with a little caution because I think this data might be a bit buggy, but besides that, we're good. So next up, we just went ahead and copied the histogram code from the teacher. Again, you do column diff, which is this one, which is the difference. Oh, we never displayed the database without it, but we're essentially just looking at the column difference and we're separating it by grade. So grade 1, 2, 3, 4, 5, 6, 7, 8, no 9, we deleted it, and then K. And in the teacher's examples, because they're a bit bigger, you first see, and I'm going to show you guys this, because in mine, again, it's not that big. I don't know how the teacher made it up, like appear a bit larger, but here you can see, so here we can see again, sorry, I wanted to pause the recording and I ended up stopping it. It happens a lot of the time. Not all the groups comply with normality, and homeostaticity was not satisfied either. But again, these are conditions you're gonna have to check during the test. This I just showed you guys to orient yourselves whenever you're practicing, but this is a very like subjective thing you guys need to be doing. Okay, so back in the mother load, what is our next step? So here's where the actual ANOVA part comes in. So you need to define our HO and our HA. So I'm going to do this two different ways. So I'm going to write them within the same one. So you're going to say that mu diff is equal to 0, or 1 second, somebody's calling me. Okay, sorry, anyways. And then you have that your mu diff is not equal to 0. So this visualized, and this is going to take a bit, so bear with me here. So you have that your mu of 1, or technically this is x bar, but let's just keep it at mu because the teacher keeps it at mu. So mu of grade 1 is equal to mu of grade 2, is equal to mu of grade 3, mu of grade 3, which is equal to mu of grade 4, is equal to mu of grade 5, 6, 7, mu of 8, and then mu of k, because we omitted 9, and I'm just gonna copy this, and we're gonna delete that, and I'm just gonna add here. Oh, that did not work. Let's just do equals mu of 2 equals mu of 3, ba, 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 ba. Or, sorry, no, this is wrong. I am, okay, ignore what I said there. Just completely ignore it. What, this is, we're actually testing that at least one pair of these, is wrong. Sorry, not wrong, is different. So say, for example, mu of 1 is 30, then mu of 2 is equal to 35, then the difference is not going to be equal to 0. But every other mu can be equal to 30. But this difference is going to tell us that at the end, the alternative hypothesis is probably more statistically significant. So yeah, ignore the fact that I was telling that all of them are different. No, the ANOVA test only looks at if at least one pair is different. So let's put this in both. At least one pair is different. So apologies for the mistake. Thankfully, I caught myself. But and yeah, I put it here in bold. So I just copied and pasted the teacher's formula because I think I can't really explain what the formula does because again, I'm not a teacher, but this is the formula you have to copy and paste. You first use OLS, you put the column you're using, and here you put the criteria you're splitting it by. So think about this as the same order as your histograms. I think that is a good way of using it. So you put diff and then by grade, and then you use your data here. And it tells you here in the teacher's annotations that you go formula and then where you're getting it. And next up, you do sm.stats ANOVA model. So this actually does the ANOVA calculation for you, which is the whole thing we saw here. It does every single one of these here for you. And then you do, this is mostly for display purposes. I'm pretty sure I can delete this so you guys don't get confused. And yeah, there we go. These are always going to appear as none because these don't have any values in the ANOVA. So you can see here, no values, absolutely no values. And yeah, that is how to do an ANOVA test using the teacher's criteria. So the only thing I think changed was our p-value, because here the teacher got a p-value of 0.01. I think that either might do with the fact, so let me test out something. And by the way, this is just me testing out something because I'm curious to why we got a different p-value. So uh so it was just Python rounding. So don't worry about it. I'm actually, let's put this here. I wanna draw, I'm gonna put a big circle here. Whenever we're off the record, that circle's there. So right now I'm just testing something because I'm gonna pause actually. I wanna test something out. Okay, never mind. I just wanted to test because if you recall, we changed the df-diff here from post percentage because this was the other way around, and I just wanted to see whether or not our p-value was different because of the rounding or because something actually changed when we flipped the post and pre percentage. The variance should be the same because at some point you would have had to square it, so it wouldn't have mattered if, like, say for example, your pre uh, god damn okay, so your pre minus post. This is I need to use my mouse. Shout out to Ali for stealing my HDMI cable. So pre minus post. If this is 35 minus 30, or sorry, minus 40, and this suddenly flips to being 40 minus 35, so this is gonna give you 5, and this should have given you -5. But once you square it, because you have to square it at some point, because you're looking at variances, if you would have squared it, they both give you 25. So I don't think that changes anything for your F and your P, but don't take my word for it. But I just wanted to give you guys a little bit of the process, and I'm gonna go back to my little off the record circle. I'm gonna put it in red. So if that circle's there, it means, guys, I might be feeding you BS. So ignore. If you want to stop the video here, that is the explanation done. But I just want to try to explain why we're using OLS. And if you go to the stats models, like documentation, and you go to OLS, this is for regression models, which regression models test. So if you do, by the way, I'm just nerding out here. So if you want to stop the video now, please go ahead. This is literally useless. Just I don't know. I might want to get to you guys' input. So if you do ordinary least squares, you're gonna see that it is a regression between an independent and dependent variable. Uh, ooh, I don't know what I touched. So yeah, this is an ordinary least squares regression. So I I want to think that we use OLS because this is the variability between groups and this is the variability within groups. But again, red circles there, oh, I accidentally clicked off of it. But if the red circle's there, um, or blue circle in this case, I might be giving you guys BS, so never take my word for it when that little circle's there, because I just wanted to nerd out a bit, try and understand. Because I don't know why we're using OLS formula. I don't know why it is this specific OLS formula. I'm gonna ask it and I'm gonna put it down in the description once I figure it out. But yeah, this video should have ended like 5 minutes ago. It was I just wanted to nerd out a little bit. But yeah, thanks as always for watching.